Okay, so we stopped yesterday by calculating this the electric field due to a tiny little charge dq. This dq is located on a portion of this ring over here, and we are trying to find the electric field at a point P. The point P, by the way, is on the axis of this ring. And the reason why this is important is because we start off by calculating the electric field due to a ring, but our eventual goal is to figure out what happens in practical electrical equipment such as a capacitor. In order to get to the capacitor, we have to sort of jump through some steps which might not seem that relevant. We found what dE was. It's K times dQ over A squared plus Z squared, where A is the radius of the ring and Z is the distance from the center of the ring to the point where we are trying to find the electric field. And what is R hat? That's the unit vector in the direction of the electric field at the point P. All right, so then we've calculated our hat by finding the full vector from the point where the charge is located to the point P, and then dividing it by the magnitude of that vector. And so we want to plug this back into this expression. So plug R hat back into this expression, and once I do that, let me scroll down. This is the expression that we get. But then we also did a quick sort of poll to figure out what the net direction of that electric field would be if I had two charges, dq1 and dq2. And the consensus in the class was that the electric field would be in the z direction. How does that come about? Well, if I had, instead of writing just dE like I wrote over here, if I had dE1 and I added it to dE2, right? So all of these prefactors, the k and a squared plus z squared and z and k hat, those are all the same for both the charges. And in fact, the dq1 and dq2, we will treat them as equal charges. So we're going to use that. So if I use all of that, then I find that the net result over here would be k over a squared plus z squared raised to the 3/2 multiplied by z k hat dq. And in fact, what happens is that the part that was dependent on the radial r hat prime vector, which is pointing like this for dq1, it's going to be pointing like that for dq2. And these two are equal and opposite, and so they're going to cancel, right? So if I add these two components, this is the result that I get. So now this makes our integral much easier. So eventually what I want to do is I want to find the net electric field at the point P by integrating over the entire ring. So now I only have to integrate over things that are constants. Okay, so if I do this integral, look, A, Z are all constants for every point on the ring. And so if I do this integral, I can pull out all the constant vectors, and I just have to write k z k hat divided by a squared plus z squared raised to the 3/2. And all I have to do is integrate over dq. So when I integrate over dq, that's just the net charge, right? If you add dq a bunch of times, integrating is the same thing as adding. So I'm basically adding dq a bunch of times until I have the full ring. So what I'm really doing is finding the net charge on the ring. And so the final answer for the ring's electric field anywhere on its axis looks like kz k hat times q ring divided by a squared plus z squared raised to the 3/2. Okay, so we know the electric field at an axial point of a ring, and we know that that's pointing that always points away from the ring. So what if I wanted to find the electric field at this point? Let me do a poll very quickly. So if I wanted to find the electric field at that point, let's do an ABCD question. Which of these four is correct? The majority choice was D, and D is indeed the correct answer. Let's highlight that. So what we found is that EP, this is the expression for EP. EP is equal to capital K, which is the Coulomb constant, times Z times Q ring, charge of the ring, divided by A squared plus Z squared raised to the 3/2 multiplied by K hat. So no matter where, like how far away, what value of Z you are at, Z is this distance. right? The distance from here to the point P, that is Z. So no matter what value of Z you are at, the electric field is always pointing in the k hat direction. But if you reverse Z, so for instance, so this is the center of the ring, which means that Z is equal to 0 at that point. So if I now go to Z negative, so you see automatically the denominator will not change because that has a Z square, but the numerator will get a negative sign, which means that if I go to the other side of the ring, then the electric field vector is going to start pointing like this. So what I want to do is I want to calculate the electric field at this point Z away from a disk. But note that a disk can be divided into tiny little rings. Okay, so what I can do is I can make an annulus like this with radius r and thickness dr. So if I take this disk over here and just look at just the cross section of it, the section from the top. So I'm looking at the disk from the top in this picture. The direction of the z-axis is just coming out of the plane of the paper. So then the annulus is just this ring over here. So if we knew what the charge on this ring was, then since we have already calculated the electric field due to a ring on the axis, we could know what the electric field due to this ring, this annulus, was. And now we could just make this disk out of tiny little annuluses. So we can just say that this little r, right, the little r changes from r equals 0 to r equals capital R, which is the radius of the full disk. And if we did that addition, we added all the contributions from all the tiny little rings, would get the electric field for the disk. And that's the idea. That's why I'm doing an integral. The integral is just replacing a continuous addition of electric fields. Okay, so the first question then would be, what is the area of the annular disk? The reason why we need to know this is because unlike a ring which had a line charge density, a disk, which is really a surface, has a surface charge density. And here we will talk about a surface charge density. We'll call it sigma. This letter over here, it's the Greek letter sigma. Okay, sigma is surface charge density. And what does it mean? It's basically a charge divided by an area. So if I know the area of a certain region, I could just multiply that area with sigma, and that would give me the charge. And if I know the charge, then I can plug it into my electric field due to a ring formula and get the electric field due to that the annulus. So first, we need to figure out the area of the annular disk. So again, I have 4 choices for you. What do I mean by the area of the annular disk? I'm really trying to find out this area. So in order to find that, since this is an annulus, what I should do is I should probably take the area of the bigger circle. So let's call that pi r plus dr squared. That would be the area of the bigger circle, the circle with radius r plus dr, and then subtract off the area of the smaller circle, which is the inner dashed circle over here, and I subtract that off. So if I subtract that off, and if you do the algebra, if you break this r plus dr squared using a plus b, the quantity squared formula, then you will see that the result that you get looks like, from here, you'll get a pi r squared plus a pi dr squared plus the term that combines the two, so the cross term, so it looks like 2 pi r dr, and then you have a negative pi r squared from the other circle. And we'll cancel these two terms, right? This is positive pi r squared, negative pi r squared, those two go away. So what you're left with looks like 2 pi r dr plus pi dr squared. So it seems like the answer is neither B nor D. But turns out in calculus, there is a certain assumption that you can always make. Quantities like dx or dy or dr, these are really small, very small quantities. So since they're very small, you can always neglect dr squared in comparison to dr. Dr squared is much, much smaller than dr. So because of this fact, since this term just has a dr in it and this term has dr squared in it, you can happily neglect this term. This term goes to 0. So the final answer is 2 pi r dr. So the final answer, the correct answer, was D, which is 2 pi r dr.
If you can neglect dr in the second term, why do you not neglect it in the first one?
Very good question. So in fact, I'm not neglecting dr in the second term. I'm neglecting dr squared. So let's say I'm doing 1 plus 0.1, and I'm taking a square of this. So what is this? This is going to be 1 squared plus 0.1 squared plus 2 times 1 times 0.1. So this looks like 1 squared is just 1. What is 0.1 squared? That's 0.01. And the second, the cross term looks like 2 times 1 times 0.1. That's 0.2. So see, what I'm talking about over here is neglecting this term relative to that term. So I'm neglecting 0.01 relative to 0.2, which makes sense, right? 0.01 is much smaller than 0.2. Now, I did this calculation with just 1 plus 0.1. The approximation is going to be much, much better if I had 1 plus, let's say, 10 to the negative 9, and I wanted to square it. So this would look like 1 square plus 10 to the negative 9 squared plus 2 times 1 times 10 to the negative 9. So there, this is going to look like 1 plus 10 to the negative 18 plus 2 times 10 to the negative 9. And here, 2 times 10 to the negative 9 is actually much larger than 10 to the negative 18. So basically, as this term gets smaller and smaller, this term, the square of that term, gets even smaller. And here, if I was just squaring 1 plus 10 to the negative 9, then I could also neglect 2 times 10 to the negative 9 relative to 1. But the magic is that I'm really subtracting off that 1 part, right? So if you remember, what we are doing is we are also subtracting off this pi r square part. So over here, if I was to subtract off the negative 1, so then this 1 and the negative 1 cancel. There, really, this is the largest term. So just remember that in calculus, these quantities, dx's, whenever you write d with something that's a tiny number, and so if you square that, you can always neglect the square relative to the thing that doesn't have a square on it. So we know the area. The area is 2 pi r dr. So if the area is 2 pi r dr, how do I find the charge? So now that we know the area of this annulus, can you tell me what the charge on this annular ring should be? Right, so we know the area. We want to find the charge. How do we find the charge? So that's, again, your question. So what is dq given that the area of this annulus is 2 pi r dr? We also know that the surface charge density, which is charge divided by area, is sigma. What is the charge on the ring? That charge is dq. What is the area of the ring? That is 2 pi r dr. So if I put that back in here, I can now rework what dq is. dq is sigma times 2 pi r dr. So really the correct answer is A. I can take this dq and plug it into my ring formula. And so I can plug it into this formula over here. So that would give me k hat, capital K, which is the Coulomb constant, times z, integral 0 to r, sigma times 2 pi r dr, divided by r squared plus z squared raised to the 3 halves. Okay, so this is just a calculus exercise because sigma is a constant. In this class, we're only dealing with constant charge distributions. So if you did that integral from 0 to capital R, you will see that the result is this. We are gonna use this information. So we've done the ring, we've done the disk. The next thing to do is infinite plane. Now you might not see this as a direct connection, but there is indeed a connection. And the connection is that if I take a disk and start increasing its radius. So in my disk problem over here, I had this disk, but now I started increasing the radius of this capital R and made that radius infinitely large. So if I make that radius infinitely large, there is no end to that disk. So it's basically the same as an infinite plane. That's the idea. Okay, so now what I can do is I can take the expression that we just learned over here, this last expression over here, and just plug in r equals infinity and see what my result is. And that will be the electric field due to an infinite plane. And we need to know what the electric field due to an infinite plane is, because that's what's going to go into calculating the electric field due to a capacitor. Again, this might not make sense yet, but soon I will explain why it sort of makes sense. Sort of. Again, in physics, we use approximations a lot, so we'll still be using some approximations, but our goal is to find the electric field due to an infinite plane. So let's move over. So I've rewritten the electric field due to a finite disk over here one more time. It's the same formula. I've just copied it over 2 pi k sigma z. I've pulled out the magnitude of z from this part. And if I pull out the magnitude of z, you can see that the formula inside those brackets becomes 1 minus magnitude of z divided by z squared plus r squared. And in order to go from the disk to the infinite plane, what do we have to do? We have to take r to infinity. So if I take capital R to infinity, you see that the prefactor here, that does not depend on capital R, so it stays the same. The only thing that depends on capital R is this part. So that grows and keeps growing. And when R becomes infinity, what happens to this, to the denominator? That denominator becomes infinity. So the denominator is infinity. So we have something that looks like some number, magnitude of z, divided by something infinitely large. So any number divided by infinity, that is equal to 0. So we get 0 over here. So this part is just gone. So our final result looks like 2 pi k sigma z divided by magnitude of z, k hat. And we can go one step further and we'll use this relationship. K is equal to 1 over 4 pi epsilon 0. Epsilon 0 is often referred to as the permittivity of free space. So Coulomb's law, if you remember, was F equals K Q1 Q2 divided by R squared R hat. F is equal to 1 over 4 pi epsilon 0 Q1 Q2 over R squared R hat. And as you can see, 1 over 4 pi epsilon 0 is a constant, so is K. So they're interchangeable. Whenever you see capital K, which is Coulomb's constant, you can replace it by 1 over 4 pi epsilon 0, where epsilon 0 is just permittivity of free space. These are just interchangeable constants. And the reason to do that is if you do this replacement, you see that this expression that looks a little bit complicated simplifies. If I put k equals 1 over 4 pi epsilon 0, the 2 pi and the 4 pi will cancel, and you'll get sigma divided by 2 epsilon 0 k hat. But you still have this z over magnitude of z hanging out. And now I want to ask the question, what is z over magnitude of z when z is 1 meter and z is negative 1 meter? And you have 4 choices again. So the first answer should correspond to z equals 1 meter. The second answer should correspond to z equals negative 1 meter. The overwhelming majority chose B as the correct answer, and it turns out B is indeed the correct answer here. There we go. B is the correct answer. If z was equal to 1 meter, z divided by magnitude of z, that's going to be 1 meter divided by magnitude of 1 meter. That's going to be just 1 plus 1. And if z was negative number, z over magnitude of z will have negative 1 meter divided by magnitude of negative 1 meter, which is just 1 meter. So negative 1 meter divided by 1 meter, and we'll get negative 1. So this is the correct answer. Okay, so what does that tell me? Tells me that if I am sitting somewhere here for an infinite plane with positive charges, then the electric field is pointing like this in the positive z direction. Remember, so what happened is E infinite plane now looks like sigma over 2 epsilon 0 k hat for z greater than 0, and it is equal to negative sigma over 2 epsilon 0 k hat for z less than 0. Which tells me that if I'm sitting at z greater than 0 relative to the infinite plane, then the electric field is pointing in that direction, in the positive z direction. But if I'm sitting at the negative of z relative to the infinite plane, then my electric field will be pointing in that direction, the negative k hat direction. Your electric field will always be pointing away from it. So in the case of the disk, this was our formula. If I went away from the disk, let's say this is my disk, and I was sitting here versus sitting here, where will the electric field be larger? So let's call this A, let's call this B. Is EA larger than EB, or EB larger than EA? So we'll do this as choice A and choice B. A was the overwhelming majority choice, and A turns out that this is the correct answer. EA is greater than EB. So why is that true? Because see, the first part of this equation, that actually doesn't depend on how far you are from the center. This distance is Z, right? Since this distance is Z, this part is always going to be the same, no matter how far away you are, because the Z's are going to cancel each other. Okay, but the second part, as you go further and further away, this term is going to decrease. Z is increasing. So if Z is increasing, this is going to make it so that this term decreases. And so the electric field due to the disk is going to decrease as you go further and further out. So now go back to the infinite plane and now give me the same answer. So let's talk about sort of a point over here and a point over here. Call it A and call it B. And we are going to ask the same question. So choice A would be EA greater than EB. Choice B would be EA less than EB. And let me put in a third choice, C, EA equal to EB. The correct answer this time is EA is equal to EB. This is the distinction between the disk and the infinite plane. So what happens with the infinite plane is that no matter how far you are from the plane, the electric field due to the plane does not depend on Z. Remember, in the other case, in the disk case, there was this second term that depended on Z. So as you increased Z, this term changed, right? This term got smaller and smaller. In the case of the infinite plane, that does not happen, right? In the case of the infinite plane, there is no second term. There's only one term. So since there's only one term, no matter where you are away from the infinite plane, the electric field stays a constant. And this is something that we use for capacitors for practical reasons. So this is what a parallel plate capacitor looks like. In a parallel plate capacitor, you have two plates, one plate like this, the other plate like that, and you put positive charges on one plate, negative charges on the other plate. And by doing so, you make sure that the electric field in the middle, in between the two plates, remains constant. Okay, constant because of the fact that electric field due to any infinite plane is a constant. It doesn't matter how far you are from the infinite plane, it stays the same. And because it doesn't matter how far you are, it also doesn't matter in which direction you go. So in fact, if you went perpendicular along the y direction over there, even there, the electric field will stay constant. All right. So there are some practical implications of this. Although we can't really make capacitors with infinite plates, right? We don't have infinite plates to make capacitors with. What we could do is we could make the size of the plates much, much larger than the relative separation between them. So we can make a parallel plate capacitor look like this, where the size of the plate, the sides of the plate are, let's say, 1 meter long, but the separation between the two plates is, let's say, 0.1 centimeter, or let's say 0.1 millimeter or something like that, right? Very, very close by. Okay, so this 0.1 millimeter is much, much smaller than 1 meter. So for anything that is in the middle over here, somewhere in the middle, something that can't see the edges, right? Something that is a point and can't see the edges that are about 1 meter away from it, to this point, these two look all but something that looks like an infinite plate, right? So basically, we're trying to mimic an infinite plate by constructing something that is constructing something out of things that are not infinite. So these are kind of practical infinities. Now, what happens at the close to the edges is something that we're not going to talk about in this course. If you're interested in it, we might be able to talk about it in an advanced course. Of course, if you go very close to the boundaries, there the electric field is not going to stay constant. It's probably going to leak out over here. So electric field lines are going to go out like that and probably come back in like this. Things like that will happen. But we're going to ignore those effects, and we're mostly going to consider the effects in the middle. And so this is where it's a good time to do a problem. I'll construct two parallel plates, and we would like to calculate the electric field. So this is the z-axis this time, right? So this is my positive z-axis. This is the negative z-axis. Let's put the first plate, which let's say there's positive charge on the first plate. Let's call the positive charge sigma. Let's put negative charge on the second plate. We'll call it negative sigma. And the first plate is at the origin. The center is at the origin, 0, 0, 0. And this one is at 1 meter along the z direction. And I'd like to find the electric field over here at this point, over here in the middle, and over here at the left side. So A, B, and C. And just like if there were 2 point charges at these 2 points, if we wanted to find the electric fields at A, B, and C, we would have found the electric field due to each of these parallel plates at these points A, B, and C, and added them together. In the point charge case, we would have found the electric fields due to each of the point charges and added them together. We're going to do the same thing here, except now we're going to use the infinite plate formula. At C, we're going to calculate EC plus and add it to EC minus. Okay, so EC plus, we know that this is due to the plus charge, the electric field is going to be pointing like that. So that's going to be equal to sigma over 2 epsilon 0 k hat. This is our z direction. For the negative charge, we would just take the negative sigma and plug it into this formula. So that would give me plus a negative sigma over 2 epsilon naught k hat. And you see that this is a positive sigma and a negative sigma. So these two really cancel and gives me 0 vector. So the electric field over here is really a null vector. Similarly, if I wanted to find the electric field at A, I'd do the same thing. EA plus vector and add it to EA minus vector. And so that's going to be sigma over 2 epsilon 0 k hat plus. So this time the electric field due to the A has a negative sign with it. Due to the plus charge is pointing in the negative z direction. Due to the negative charge, that's pointing in the positive z direction. So that's really, there is a minus over here, but there's also an additional minus over there, k hat over 2 epsilon 0. If I add these two together, what I get looks like negative sigma, positive sigma. So this is again 0. So the electric field over here is 0. Okay, so now we want to find the electric field in the middle. So what we are going to do is EB plus vector plus EB minus vector. And I'm going to let you do this exercise. Which one of these 5 is correct for the net electric field at the point B, where B is in between the two plates? Take a little bit of time to actually calculate it, like I did in the first 2 cases where I put in E plus for C, E minus for C, and added them. There's a 3-way tie between A, C, and E. Really, the answer here is C. And the reason for that is, again, what we would do in order to find the electric field at B is take EB plus and add it to EB minus. So what is EB plus? Well, EB plus, we see that B is along the positive z direction compared to plus charge. So z is greater than 0. So we're going to apply this first, the top formula. We'll write sigma over 2 epsilon 0 k hat. Due to this positive plate, the electric field is pointing like that. For the negative plate is also going to be attractive, so it's going to point like that. So for the negative plate, it's really behind the negative plate, so it's the bottom formula that applies, but the bottom formula with a negative sigma, because the charge itself is negative. So what it looks like is negative sigma divided by 2 epsilon naught k hat. So this negative and that negative cancel becomes a positive. So what we get is now the effect of adding these two, 1/2 plus 1/2 is 1. So we get sigma over epsilon naught k hat. So that's the net effect of adding the two vectors. So that's why C is the correct answer. So flux of a field is how much of the field passes through an area. So this is a new term that we are defining right now. So flux is represented by this letter phi, or phi if you like, the Greek letter phi. And so we have talked about electric fields. We know what an area is. I'm going to define an additional quantity which I'll call the area normal. You should have seen this at least in physics 1. So we'll talk about that area normal very soon to represent an area vector. So generally, whenever there is an electric field, we need to know how many electric field lines are crossing some area, and that's going to be given by this quantity called flux. Okay, so flux of a field is how much of the field is passing through an area. So for instance, in this picture, there's this area, and there are electric field lines that are passing through this area, right? So we want to find out how much of that is passing through that area. That's what's going to be represented by flux. Similarly, in this picture, here the electric field kind of looks like the same everywhere, but here the electric field is changing in different directions. It's in different directions. And the green surface is the surface that we're interested in, and we want to find how many of these field lines are crossing that area. And that's what's going to be given by flux. So question 1, same electric field. So this picture is showing you the same electric field, and when you see the distribution of these electric field lines, that has to do with how strong the electric field is. Often that is also referred to as the strength of the electric field. So if you have more lines in a given area, that is a stronger electric field. So over here, it looks like the electric field on the left side and the right side, they are the same because they're the same number of electric field lines, and they're also constant in the region that they're in. And assume that in each of these two figures, in the first figure or the second figure, the electric field is passing through this area. But the areas are different. A2 is actually larger than A1. And my question is, which of these two is correct? Is the choice A correct or choice B correct? Turns out B is the correct answer. The idea is that if you have a larger area, more of these lines will cross that area for larger area. So remember that. Electric flux is larger for larger area. Okay, so it's kind of looking like if I wanted to write an expression, so phi or phi is proportional to the area, given that the electric field is the same. E is the same, flux increases with area, right? That's our result from this question. Let's do the next question. So again, now this time I have two different electric fields, but the same area, right? Same area, but different electric fields. E represents the magnitude of the electric field E, and phi represents the flux. Which of these is correct? I'm expecting that you will also tell me about which one of these electric fields is larger, and of course, which one of the fluxes is larger. And D, as you see, was the majority choice. And it turns out that D is the correct answer. Electric field is larger. E1 is larger than E2. And how do we know that? Clearly, there are more field lines over here compared to here. And as you can see, this is the same area. Per unit area, E1 has more number of lines of field than E2, so E1 is larger than E2. And if E is larger, A is the same, then flux is larger. Phi is proportional to the electric field as well. So as the electric field increases, phi or phi increases. The flux increases as the electric field increases. Okay, so we got really two answers from those two parts. Flux increases as the area increases, flux increases as the electric field increases. Just to remind you, there were really three things. One was the electric field, the second was the area, the third was the area normal. So we have three figures in these three parts. There are three figures, and again, what I'm expecting is that you're going to tell me where is the flux maximum or a minimum. Essentially, you're going to pick one of these four choices. So question is, which one of these is correct? Again, remember what flux is. Flux is how many number of field lines or electric field lines, these arrows, are crossing an area. So if you look at this picture, in this third picture, the one to the right, all of these electric field lines look like they're parallel to the area. So it's not going to be possible for these lines of force to enter this area, right? On the other hand, over here, all of these electric field lines are going to cross this area. And over here in the middle, some of these electric field lines are going to cross, some of these are not going to cross, which means that flux for this left-hand side is going to be the largest. Flux for the middle one is going to be somewhere in the middle. Flux for this last one, this right-hand side one, is basically going to be 0. So phi right is the least. So phi right is the least. Phi mid is then the larger one, and phi left is the largest one. So C is the correct answer. Okay, so what is this telling you? You see that with the area, I have also drawn the area normal. So it looks like if the normal to the area is parallel to the electric field, you have the largest flux. If the normal to the area is not parallel to the electric field, you have slightly less flux. And if the normal to the area is perpendicular to the electric field, then the flux is 0. So what can we think about that behaves like that? What if I write this quantity, electric field, E, and then I take a dot product of this with the area normal? Okay, so if I take the electric field and dot it with the area normal, is magnitude of E, which is just E, magnitude of n hat, which is 1, because n hat is just a normal unit vector, right? So since it's a unit vector, its magnitude is 1, multiplied by cosine of this angle, theta. Okay, so E dot n is just E cosine theta. And if I put in theta equals 90 degrees, meaning that theta equals 90 degrees means that the area normal is perpendicular to the electric field. If theta is equal to 90 degrees, what is cosine of theta? Cosine of theta for 90 degrees. And this is the advantage of doing things using a calculator, is that it can tell us what the answer is. Cosine of 90 degrees is actually 0. So if I plug in 0 over here, I get 0 for the flux. So it turns out that this is a good quantity to represent flux. Okay, but remember, flux is also proportional to the area, right? So if I go backward, remember, flux is also proportional to area. It's proportional to the electric field. And now we are finding that it should be proportional to this quantity E dot n. The electric flux looks like phi equals Well, it should be proportional to, we decided that it was proportional to the area. It's proportional to the electric field, magnitude of the electric field. And we also decided that it was proportional to E dot n hat. Then I can kind of write phi equals E dot n hat times A. And sometimes it's also written as E dot A, with the idea that the area vector looks like the magnitude of the area times the area normal vector, or the normal vector is just a unit vector. So what is the definition of flux? Flux is equal to electric field dotted with the area vector, where the area vector is defined as magnitude of the area times the normal unit vector. You're going to find the flux through a cube. So this is going to be a ranking task. So I have 6 different sides of this cube, A, B, C, D, E, F. So A is the side over here, B is the side over here, and so on and so forth. And we want to figure out what is the flux through each side when there is an electric field that is everywhere. So this electric field is everywhere, going everywhere through that cube. So if I want to find the flux through that through each of these areas, what I'd have to do is figure out the area normal vector each time. So for example, over here for the surface C, the area normal vector looks like this. Okay, so in the picture I've called that this direction, the x-axis. So this n hat is also equal to the I hat vector, the unit vector along the x direction. And from the picture, it looks like the electric field is also pointing along the x direction. So in our picture, E vector is just equal to E times I hat. So now if I wanted to find the flux through the surface C, that phi C is going to be equal to E dot area vector. So E dot area vector, let's say that the length of this side of the cube is just L, so the area is L squared. So we will get E times E I hat dotted with L squared times I hat. I hat dot I hat is 1, so we'll get E L squared. So that's the flux through C. If I wanted to do the same thing through A, remember that the surface of A is pointing outward like that. So that's pointing along the negative I hat direction. So this time if I wanted to find phi A, that's going to be equal to E dot. So just to distinguish, we'll call that AC and this one AA. So this is going to look like E times I hat dotted with negative L squared I hat. The negative L squared coming from the fact that the area vector for this side of the cube is pointing in the negative I hat direction. So that's going to be equal to negative E L squared. So that's for A and C. Let's do it for B and F. So if I wanted to do it for B, B is the normal vector is pointing like this. For F, the normal vector is pointing like that. And if I wanted to do it for D and E, for D, the normal vector is pointing like that. For E, the normal vector is pointing like that. So for F, so phi F is going to look like E vector dot A F. And E is the same, E is E I hat. But remember, since this is a cube, the lengths are all the same. So the area of F is still L squared, but the vector in which F is pointing is along the Z direction. So this should be K hat. And if you remember your physics 1 class one more time, I hat dot K hat was 0 because I hat and K hat are perpendicular to each other. Two perpendicular vectors, if you take the dot product, you get a 0. So this answer is just 0. And similarly, if I wanted to do phi, I don't know, phi B, again, E dot AB. Okay, so if I go back over here, B is pointing downward in the Z hat direction. So this is going to be E I hat dotted with negative L squared K hat. And this is also going to be 0. And in fact, you can see the other two vectors, the normal vector for the D and the normal vector for the E, these are also pointing along the Y hat direction, and I hat dot J hat is also 0. So the other two fluxes, the fluxes for E and D will also be equal to 0. So if I wanted to do this ranking task over here, we will say phi C or phi A is equal to phi C. These are the largest. And then everything else is the same. Phi F is equal to phi B is equal to phi E equals to phi D.
Wouldn't phi C be less than phi F, B, E, and D since it's negative?
You were right. What I should have written is, let's see if I can do that. Thank you for correcting me. So here we are seeing that phi A is the least, phi C is the largest, right? So phi C, phi A. Good? Does that make sense? If, on the other hand, we were ranking just the magnitudes, then what I had written earlier would have been correct. So what is the net flux through this cube, though? So in order to find the net flux, we'll have to add it all together. And you see that if I add it all together, phi C and phi A are opposite to each other. So if I add these two together, I'll get a 0. And if I add these together, I'll also get a 0. So the net flux, phi net is equal to 0. Okay, great. What if instead of this situation where there's a constant electric field, I still have a constant electric field, but that, let's say that the constant electric field comes from an infinite plate which is stuck in the middle. Okay, so just to remind you what the electric field due to an infinite plate was. So if, let's say, the charge density on the plate is sigma, then the electric field on that plate E is equal to, and let's say that this time, well, let's keep the convention that I had set up over here. This is still the x direction. So since that's the x direction, the electric field over here on this surface of this cube, so surface C of the cube, looks like E is equal to sigma over 2 epsilon 0 I hat. And on this back surface, the A surface, that electric field is equal to negative sigma over 2 epsilon 0 I hat. Okay, so this is EC, this is EA. Okay, so the electric field is constant and it's always parallel to the x direction in this picture, which means that if I try to find the flux through any other surface other than A and C, I'll still get a 0, just like the previous case, which means that if I wanted to write here phi B will be equal to phi E, or phi D equals phi E is equal to phi F, these will still be 0. Okay, but this time, if I wanted to calculate the flux for C and A, so for C and A, if I did phi C first, phi C is equal to EC dot AC, and AC, as we wrote before, it's L squared times I hat. So if I plug that in, I'll get sigma over 2 epsilon 0 L squared. I hat dot I hat is 1, so this is the answer. And if I did phi A, that's going to be EA times AA. Now notice that EA and AA both have the negative sign. So sigma over 2 epsilon 0 I hat dotted with negative L squared I hat. Okay, so if I take this dot product, I still get sigma over 2 epsilon 0 L squared. And I hat dot I hat is just 1. The negative signs cancel. So this time, what I can write really is phi C is equal to phi A is greater than the other form. So what happened is that if I put an infinite plate in the middle of a cube, rather than just having a constant electric field, suddenly the fluxes don't add up to 0 anymore. There is actually a net flux. If I now add all of these fluxes, phi net is going to turn out to be equal to, if I add all of these fluxes, B, D, E, F still contribute to 0, but these two together contribute to something that looks like sigma over epsilon 0 L squared. Because I just add these two together, the 1/2 plus the 1/2 gives you a 1. And this brings me to something that is very interesting. We'll come back to this in our next class. So if you look at sigma times L squared, that's basically the charge that is on the grayed out area in the middle over there, right? So I can replace that by what I will call Q enclosed. So that's all of the charge that is inside the square. So it looks like phi net is equal to Q enclosed divided by epsilon 0. And this formula is referred to as Gauss's law. We did it for an infinite plate, but turns out to be true for any sort of charge distribution. In fact, it's true over here as well, in the first situation as well, because in the first situation, this box, the cube, did not have any enclosed charge. So since it didn't have any enclosed charge, the enclosed charge in this first case, Q enclosed, is equal to 0. So if I just take that Q enclosed equals 0 and plug it in to my Gauss's law formula, then I still get phi net is equal to 0, like we found, right? So this is an important formula. This formula phi net is equal to Q enclosed divided by epsilon naught. This is an important formula. It's referred to as Gauss's law.